Kohei, thank you so much for taking this time today to share your insights with us, and we look forward to your remarks. Thank you.
So thank you so much, Annelise, for the wonderful introduction, and I'm so happy to be here. And also, please accept my condolences for those who lost your families, loved ones, important ones on 9/11. It was a great shock for us, and it happened so that I'm here on 9/11. So I had to say this first. Anyway, so let me start my opening remarks, and I have three parts. One is just to introduce quickly who we are and let me see, it doesn't move forward. Okay, just to give you who we are. Keio Gijuku, Keio school system is composed of elementary school all the way to graduate school, and also we have hospital. So they are all in one system, and I'm serving as a chair of the entire system. So I have a responsibility to oversee everything. But at the same time, I'm serving as a president for the university and the graduate school. And Keio was established in 1858. It's composed of the 10 undergraduate faculties, and we have 14 graduate schools. We have more than 3,300 students and close to 3,000 faculty members. It's a big school. We have 6 campuses concentrating around central Tokyo. And just to give you an idea, we have 10 undergraduate faculties: letters, economics, law, business and commerce, medicine, science and technology, policy management, and all the way to pharmacy. And we have 11 graduate schools. As you can see here, I won't read out each one of them, but just to give you the flavor of who we are. Okay. And last slide on Keio University. As explained already by Annelise. Annelise, where are you? Somewhere. Where are you? Yeah, maybe you were taking. Back in the back. Okay. And also Megan was here. And then here's the time when we submitted our proposal to our Prime Minister Kishida. And our proposal on how education should be was reflected on the communique of the G7 Hiroshima Summit this year. So this was a lot of work, and it was very rewarding work. So, and also about 10% of the politicians in Japan, upper and lower house members, are graduates of Keio University. So we have quite some influence in politicians, Japanese politics. We have also the largest number of the CEOs in, let's say, Nikkei 225 and all these important index companies. So we are strong in both business and politics, but also we're pushing our engineering and medicine front quite strongly. So I will now talk about quantum computing. Okay. So why quantum computing? Quantum computer is computer. So I have to first introduce what computer is, right? And quantum computer, the best computer, probably you can naively say that's a supercomputer. So there are supercomputers, but in the heart of supercomputer, that silicon chips are working as a processor. So silicon chips are really the computing device, processing device. And silicon chip, as you know, started from a few number of transistors in 1960s, but now it's reaching to hundreds of millions of transistors integrated into one chip. And this integration really has been enhancing the power of the computing, okay? And 25 years ago, 1998, I was staring at this trend called Moore's Law. It's a roadmap for advancing silicon chips. And it says that by 2030, the transistor will be the size of the atom. So in 7 years, it will reach the size of the atom. And what does it mean? What does it mean? Why had we been shrinking transistors so eagerly? Well, smaller transistors leads to faster computer. So I will give you the 1-minute crash course on transistor, okay? Computer only uses 0 and 1 binary. Well, we usually use 0 to 9, right? I need 3 cups of coffee in the morning, let's say, 3, okay? 3 or 4, let's say 4 is 100 in binary number, okay? And 0 and 1 processing unit is needed, and it is used in computer, and it is called bit, 0 or 1. And such bit is represented by one transistor in silicon chip. And transistor is an electrical current on and off switching device. So it changes between 0 and 1 because transistor current off is 0 and on is 1. So transistor has a simple structure. It has a start of the current and goal of the current. And when the current, and there's a switch. So when current is on, it's 0. It is 1. Just for the simplicity, I just say, when the current is on, it's 1. When the current is 0, it's off. So how do you, then switching speed determines the calculation speed. How quickly you can switch on and off is a power, determines the power of the computing, okay? So how do you make it faster? Simple, in a simple-minded picture, you make the distance from the start to goal shorter, right? It's simple as that. You said go, switch goes go, and then electrical current starts to flow. And when it reaches the goal, it knows that it's 1. So shorter the distance, faster the switching you can make. And also the shorter the distance, the less energy it takes. So you can actually reduce the power consumption. So faster computing with less power can be achieved by just simply making this distance smaller and smaller. And by 2030, this distance will become the size of the atom. So 25 years ago, when I saw this trend, I have to think about the way to make one atom calculation in silicon. And that's how I started my quantum computing research, because when you have to think about one atom calculation in silicon, you have to change your mindset completely, because there's no start to the goal. And I start to think about using each atom in silicon as a magnet, and magnetic direction. Pointing north is 0, pointing south is 1. So this is just simple magnet direction calculation by atom, or even by single electron placed in silicon. So the whole idea is to use a single atom or single electron magnetic property as for calculation. So it sounds very simple. This magnet pointing north is 0, magnet pointing south is 1. But can you actually perform such calculation using single atom or single electron is a big physics question or chemistry question and so on. And can you actually place such atom or electron at the desired position so that you can actually perform huge number of calculations? That was the challenge I found 25 years, and that's this challenge I decided to, pursue 25 years ago. But there's one more important thing, and when you actually dealing with magnet of the atomic size, you are no longer dealing with 0 or 1, but now you have to deal with 0 and 1 at the same time. So if the magnet is pointing sideways instead of up or down, sideways, it is 0 and 1 at the same time. This is a quantum mechanical property. And because of this so-called superposition, the quantum computer property is achieved, okay? 0, so in a classical term, in a transistor, it was always 0 or 1. But now we have 0 and 1 at the same time. It's very counterintuitive. Let's say you have a bottle of wine, and you were told this is white and red at the same time. It's not the rosé, okay? It's a red and white at the same time. And you only know when you actually open it. But also, the wine itself determines either 0 or red only when it opens it. Until it opens it, you open it, it's either white or red. It's just very counterintuitive, but this is the property we can achieve, we can get in a quantum mechanical world. Okay, so what do you get? And then once you accept such condition exists, and the rest of the thing you need to do is the same as other computing. You put all these magnets in an array, set everything in 0, and you perform calculation according to algorithms or software, and then at the end you just read out each sort of bit 0 or 1. That's all you need to do in a quantum calculation. But the strength comes in the so-called quantum parallelism. So if I have 3 bits quantum computers, then it is 0, 0, 0, 0, 0, 1, all the way to 1, 1, 1 at the same time. So only with 3 electron spins or atoms, we get 8 different kinds of numbers same time, right? Then if you have, let's say, 280 of those magnets, then you can get 2 to the 218 numbers at the same time, which is 10 to the 10 multiply 83 times, which is same number as a number of atoms in the universe. So you can try all sorts of variations, all simultaneously in quantum computing. So quantum computer is useful, especially when you have to try all sorts of different variations, okay? So we try all sorts of physics, material science. We demonstrated that we can actually form an array of the 29 silicon magnetic silicon formation and so on. Each atom you see here, each spot you see here is a single silicon atom. So this was performing my research lab. 2011, we were able to perform the proof of concept demonstration of such magnetic computing in silicon. This was actually a big news in New York Times as well. And then 2015, we were able to demonstrate the true silicon quantum computing with 2 electron magnets using the structure manufactured by standard silicon technology. So we went up to 2 qubits, and then after that, we transfer such sort of ideas to Intel, because for us to move on to 10 qubits and 100 qubits, we've already demonstrated a proof of concept. So we say rest is the job of the industry. So we somewhat graduated. And so this was a graduation ceremony at Intel. Our 4 quantum computing teams, one from New South Wales in Australia. My partner also comes from University College London in UK, and Simon Fraser University in Canada. So we were very proud of this graduation ceremony at Intel. Of course, silicon actually is not the only quantum computer platform. In fact, superconducting circuit was the quantum ahead of silicon. And that actually came up as a commercial product around 2017. Google, Intel, RIKEN, IBM is a big one, Rigetti, and so on. Those are the, now we have more companies making such superconducting qubit supercomputers. And they're making those computers available to many academic institutions. So in 2018, after our graduation from hardware research, we switched our research to algorithm and software, and we team up with IBM Watson Research Laboratory to work together between Keio and IBM. So what we do is that we have this hub at Keio University, and we have actually 9 companies currently working with us. So they are financially supporting our hub, but also they are sending their best scientists full-time at Keio University. So we have about 30 scientists working full-time with us at Keio University. And then we actually, our postdocs and researchers work together with those researchers to make use cases, how to utilize quantum computers, kind of a research. So this is the state of art and the forefront of the applications of the quantum computer I'm going to discuss. So we have the Keio faculty members of the different disciplines participating on this research. We have the postdocs hiring, working with us, and we have the company researchers, and we have IBM researchers. We have more lists, but I can't. We don't have enough space to show. But basically, we have all these people working full time at Keio University. So in the last 5 minutes or so, I just want to show you what kind of sort of applications we are developing. So and just one more thing. So I talk about Moore's law for silicon electronics. Now, after witnessing the development of IBM quantum computers since 2017, that's when we actually started working on IBM. IBM quantum computer has been advancing with the exponential rate, just like Moore's law. So we can actually safely predict how IBM quantum computer will grow in the near future. So we have the Moore's law of the quantum computers, and that's important because when we actually develop a software algorithm and so on, we know that, let's say, this algorithm will be useful in 10 years. 10 years, it will actually surpass, for example, the performance of the supercomputer in 10 years, right? So this is our roadmap. And one application we actually developed is that 3 banks work together with us. And banks bring in so many of the challenges they have. One challenge we were surprised about is that, let's say you're a bank and you're given $1 million US, and you were asked to transfer such $1 million to euro within the next 24 hours. What does bank do? It spend first 8 hours performing so-called Monte Carlo calculation to find out at which moment in next 24 hours the yen is strongest against euro, right? Because you have $1 million, right? But it spends for 8 hours. So you throw away first 8 hours. And bank said, we need to be quicker. And Monte Carlo is a calculation you perform with trying all sorts of different variations, all sorts of different scenarios, and then you average them out to achieve the precision you need. So variation when there are too many variations, computation takes too much time. But I told you already that quantum computer can try all sorts of variations in parallel. So we came up with the algorithms and software to solve such problem. Right now, of course, today's computer can do much better, only because IBM quantum computer is still at the stage of the kindergarten. It's been 4 years, right? But in 7 years, for example, they will be in high school level. And when they're in high school level, and then what we are doing is really the parenting, right? IBM is responsible for the physical growth of the quantum computer, and we are educating the quantum computer. So we know by when this might be useful with respect to the future of the supercomputer. Next example is that bankers wanted to know the stock share correlation in a stock share correlation is that, okay, here's a simple example. When United Airlines share price goes up, intuitively you know that so does the share price of the American airline, for example, because they're in the same they're in the same category. But maybe maybe there's a correlation exists between airline and something completely different. I don't know, candy company. And those bankers want to find out hidden correlation between pairs of sort of counterintuitive pairs, if there's any correlation between stock price. But then they want to try out mapping, try out to see pairs of all sorts of variations. But there are too many companies in the stock market, so there are too many variations. But we came out with this way to calculate such problem using quantum computer. And by doing so, we have actually demonstrated that possibly in 8 years, we can actually use quantum computers. Possibly in 8 years, meaning that in 8 years, if the IBM quantum computer or other quantum computer grows as we expected, then we can actually find such hidden correlation in stock market. And hidden correlation is something that the bankers are looking into. But we scientists are always looking into hidden correlations between parameters, right? So in our data we have. So this is something that we always also want to tackle, using quantum computer for scientific discoveries and so on. So this is another thing that we're trying to do. AI, there's a problem to tell between panda and gorilla. And people actually throwing all sorts of gorilla picture and then panda picture into AI and AI to train AI. And somehow these blue dots are panda, red dots are gorilla. So this is a part of the training to draw clear border between those two. So next time you throw in picture, the AI will tell it's either panda or gorilla. And this is already becoming more and more difficult for two species that are very difficult to tell. And for this kind of problem of drawing clear borders, we've shown for the first time that we can also use quantum computers. And this was demonstrated by quantum computers here, by IBM. And again, with the growth of IBM quantum computers and other quantum computers, we think we can actually utilize them in the future. Okay, so rest of we have three more examples and I will complete my introduction. Basically telling the difference in shape between ABC. We have the actual sensor. Again, they are clearly different shapes from that you can tell that they're clearly different shapes. But if they look very similar and difficult to tell, then it becomes a very difficult computational challenge. So in the future, we would like to do that with a quantum computer, and we've found a way to do that with a quantum computer as well. Last one, this is really the field of Mike. We are also using the quantum computer to understand the property of molecules. For example, we have an application to chemistry to design, which molecule illuminate the most or has a longer lifetime and so on, for display application and so on. That's a demand of the chemical company that we have in our membership. And sometimes they try to substitute those hydrogen with deuterium, heavier hydrogen, and try to see which which hydrogen to be replaced with a deuterium. Heavier hydrogen is efficient for, I don't know, for longer life or better light emission and so on. So this is also something that we are calculating with we are calculating with a quantum computer. And with today's quantum computer development, even with this, quantum computer can do much better than the extension of the supercomputer. But even quantum computer can only reach the rigorous, for example, simulation of water by, right now we can do the simulation of water, but we can only do the rigorous simulation of CO2 by 2026 and slightly bigger atom by 2030. This is very slow. So we want to accelerate such research by putting more effort and people together. But at the same time, we are heading into bigger picture in the sense that all these quantum computer people, supercomputer people, semiconductor people, AI people are working closely with the medical staff, microbiome, metabolomists, and organoids, and so on, so that we can really explore using AI, supercomputer, quantum computer, all these together to understand the big data we have in a Keio School of Medicine and so on. So with this, I will stop. But basically, I think the earliest application will probably emerge in 2027 or so, hopefully. So we'll see how it goes. Thank you.
Thank you, Professor Itoh. As Annelise already mentioned, I'm Mike Wasielewski, and I am currently the director of the Initiative for Quantum Information Research and Engineering at Northwestern. And what I'd like to do is tell you for a couple of minutes what is going on regionally here. We're particularly fortunate in the Midwestern part of the US, especially in Illinois, that we've become a very large hub for this kind of activity. And first of all, the Department of Energy has funded two major research hubs, one at Fermilab, the Superconducting Quantum Materials and Systems Hub, and the hub called QNext at the Argonne National Laboratory, each of which involve numerous principal investigators, not only at the labs, but at affiliated universities. And Northwestern itself has a very large contingent of people involved in this particular activity. As the name implies, SQMS focuses on superconducting materials, which form the basis, for instance, of the IBM and Google embodiments of quantum computers, whereas QNext is more broadly based and is focused on many, many different technological approaches, including defect centers in, for instance, diamond and silicon carbide. As in in addition to other more broadly based technologies. Also, we have Energy Frontier Research Centers, also funded by the Department of Energy, including the Center for Molecular Quantum Transduction here at Northwestern and a Materials Center at the University of Illinois in Urbana-Champaign as well. Here at Northwestern, CMQT is involved largely in taking advantage of the quantum properties of molecular systems in order to be able to move information from one type of quantum environment to another. For instance, from light, from photons to electron spins. And so this really focuses our efforts in the two other major areas of quantum information, that is quantum sensing and quantum communications. Quantum sensing has a lot of really near-term promise, especially when you consider the superposition states that Professor Itoh has described so eloquently. Those superposition states in molecules, for instance, are exquisitely sensitive to the environment around a molecule. So if you can imagine, for instance, being able to detect a single protein using a molecule that is in a superposition state and having the two associate with each other in a way that is absolutely unique. So you could get single molecule specificity in analysis of disease states, for instance. That I think is coming quite quickly, probably in the next 5 to 10 years at most. The idea of quantum communications, we all kind of point to the fact that ground to satellite communications with entangled photons has been demonstrated even in 2017. But communications is more than just long-range communications. It can be communications between quantum processors on a nanometer scale. In other words, on very small length scales that are needed in order to make these small processors communicate with each other in the ways that promote quantum networking. So there are many, many applications in this area that I think broaden the base of activities that are available to us and essentially from an intellectual standpoint, allow us to bring together the physicist, the chemist, the material scientist, and the biologist even to really take advantage of this emerging new technology in ways that will benefit society in general. So I think that's really where all this is going. And I think now we'll simply open it up for some discussion.
Thank you. Mike, why don't you sit right here in the middle? Okay, great. So a lot to talk about, and I have to admit that I'm one of those people who needed the crash course. So if anyone else is in that position, you're not alone. Okay, so this is super interesting. I guess I'd like to just start by asking Kohei if you have any remarks or reactions to what Mike just said.
Oh, this was a wonderful and very precise overview of the quantum technology, just in state of art in quantum technology. I mean, I have been involved in quantum sensing. I have not been involved in quantum communication, but I'm actually leading the policy making on quantum technology in Japan. So the type of description, actually he does much better than I, but type of description is something that I deliver all the time to general public, and this was really professional.
And would you agree with his assessment of Mike's assessment of where things are going and the timeline and so forth?
Yes.
Okay.
Yes.
Great. Interesting. And Mike, you would agree with the assessment of the timeline and so forth that?
Oh, yeah, definitely.
Kohei?
I think things will be much more aggressive with regard to quantum computing in the next 5, 10, 15 years. And I think that aggressive timeline is needed if we're really going to, have a serious goal of making this happen for all these applications that are waiting out there.
Okay, so since this is the Buffett Institute for Global Affairs, I have to ask you a question about global affairs. So we're facing all these giant global challenges now: climate change, pandemics, more migration than we've seen at any other time, inequality, we could go on and on. war. When you think about these big global problems, do you see what kinds of applications or implications do you see of this development for addressing any of those challenges?
Okay, one thing I forgot to mention is that quantum computing will not replace today's computer. In fact, today's computer, supercomputer, AI, everything based on silicon chip, will be the dominant um, computing platform for many years to come. However, just some of the problems that are not possible with today's computing scheme, especially those that requires trying all sorts of variation, too many variations. I think that kind of a mission impossible for the today's extension to today's computer may be able to, it might be able to solve by quantum computing. And this is our approach, so that quantum computer will be the supplement to today's computing. But even so, if we can actually solve the problem that is impossible by extension of today's computer, that will contribute to the overall advancement in computing. And so it's not the story of the quantum computer alone, but we should really talk in the framework of the computer in general.
Okay, but in your talk, Kohei, you talked about some applications that banks have to basically
yes.
increase their profit margin. But I'm wondering if you have in mind any mission impossible problems in the realm of addressing our great global challenges, like the pandemic or so on, that you think could be relevant.
So it's just that there are problems that cannot be solved by today's computer. And this is why we try to increase the power of the computer. However, as I said, if you actually try to stick to the Moore's law, then by, I don't know, in 7 years or so, it will hit the size of the atom, which means that Moore's law cannot, no longer can sustain the advancement of the computer. So we have to come up with something different to keep the advancement of the computer that is predicted by Moore's law. And to do so, today's computer needs every help. And one help can be the quantum computer. And when the computer grows, then global problem like, I don't know, global warming or other issues may be able to solve by the advancement of the computing in general. So it's not the specific to quantum computer, but advancement of the computing is very important to solve whatever the problem we have at this point.
Yeah, I would agree with that. In fact, if you think about it, just wearing my other hat in the energy and sustainability space, climate prediction and climate modeling are really important areas in terms of trying to address both the climate change problem and associated issues. And certainly the complexity of those, or and the scale of that type of simulation is large enough that it could benefit from quantum computing applications. And one can always quote Richard Feynman's famous assertion that the best problems that a quantum computer could solve are quantum problems. And in point of fact, molecular design and design of interesting new materials and even drug design would benefit greatly from being able to do computational chemistry at a level that is far more precise on larger and larger systems that quantum computing can offer.
So now I want to ask you about the flip side. Are there any dangers or concerns that you have about this technology as it's evolving? Anything that's on your mind that we should be thinking about, either from a regulatory point of view or an ethics point of view or anything else?
So it's just, again, it's the same question as what's the ethical danger of advancement of computing? And currently, the supercomputer or the more advanced computers spend so much, consume so much energy. So data center, for example, and we use Google and other data search, and they are all and Google's data center and so on, and they are using huge amount of electricity. Quantum computer on the other side uses much less energy. Um, but for example, Japan's supercomputer uh, called named Fugaku, it uses 1/10 of one atomic power plant, and that's how much energy it uses. And then so is a Summit supercomputer in the U.S. So in order to achieve such computational power, it requires so much electricity consumption. However, quantum computer that we are using is can be just run in the electricity of this room, for example. So it's actually super power sort of efficient computing. However, it can only do very small amount of part of the problem of the big problem we have for the computing. So, but still, um, replacing some of the problems that supercomputer is performing can also lead to less energy consumption.
What do you think, Mike?
Well, I think one of the fun examples is I believe Google has been siting their data server farms in the Chilean desert so that they can get solar energy 365 days a year. And so it's really endemic or emblematic, I should say, of the kind of power needs that you already mentioned. And so I think that's an issue. I think one of the other sort of subtle issues that we have to face, though, is right now quantum computers require ultra cold temperatures. So the question is, if they're going to become technologically ubiquitous in our society, we need to somehow be able to raise the temperature in which they work. And so the question then becomes, how do we do that?
Interesting. So maybe just the last question before we open it up. You're both incredible innovators in this space, really boundary breakers. So I'm wondering if you could talk a little bit about what you've learned about what makes for innovation in this field. What kinds of teams are needed? What kinds of training do we need our scientists to have? Maybe even what space would there be for collaboration between, say, a top-ranked Japanese university and a top-ranked American university in this space?
Students are full of curiosity, and also are the postdocs and other scientists. So we, as principal investigator, or we who actually lead scientific lab, needs to come up with interesting enough scientific question, but also interesting enough scientific goal. So 25 years ago, as I said, when I actually saw the trend in silicon chips, I saw that, okay, we have to come up with a solution of performing calculation using single atom in silicon. That's when students who were looking around to see which labs to join were were actually quite excited with our research, because it's a far reaching goal, but still everybody was very excited about this idea of shooting for something that we need to do by 2030, but also physics problem wise, this is a very interesting question, because whether we can actually rely on quantum mechanics to control the property of the atom, and whether we have the technology to do it, and whether we can develop the nanotechnology to manipulate the position of the single atom, and we have the sensor technology to read out the magnet, single atom magnet, that is so weak. So whether we can achieve such sensitivity. Already Mike mentioned that the quantum sensing is one way to go. But those kind of a combination of the forefront of the science and technology was something that our team was very attracted to. And that actually kept all of us going. And, we were aiming for the goal of the 2030, but we achieved this by 2015. So I was able to move on to different kind of a research. Yes.
I think that's right. And I also think that students and postdocs need to be encouraged to pursue the hardest problems possible and to sort of avoid the minutiae and the details and just go after the toughest questions out there. On another point, too, I think establishing a culture of team science is really very important. In order to do this, students need to be given the freedom to be very multidisciplinary, to not only become experts, but also be conversant in many, many different fields. In other words, be problem oriented and bring to bear whatever on a problem you need to bring, rather than being siloed into one or two or three different specific areas. So this idea of team culture is extremely important in all science, but in this area especially, because it requires a broad-based knowledge. And I think, certainly here at Northwestern, we have had this culture for many, many years, and that culture has really been part of the driver in all of the science and engineering fields that are represented here. And it was that way even before, for instance, funding opportunities actually required it. And so we were well positioned with the culture here to really give our students and coworkers an experience that I think is important in solving these problems.
It's fascinating and
So
fantastic.
one of the conferences I attended in, let's say, 2010, I presented our teamwork on silicon quantum computing. And one of the prominent scientists after my talk came to me and asked me, so how many slaves do you have to put all these results together? Now, I didn't understand the question, but he thought I was ordering every student to do this and that and that and that to put them together. What I was doing was exactly opposite. I just said, we need to achieve this. What do you think? And they say, yeah, that's interesting. So you just do whatever you want. And then the students try different things freely. And this is how they were so much interested. And all I did was just put those results of the students and postdoc together as if I ordered them to do. And that's a very different, very similar environment to just what Mike described, because it's this kind of a academic and also forward-looking, educational, but we're also asking them to try their best for very challenging problems. So sometimes they worry about whether they can really get PhD with such difficult project, but they always come through.
No, I think that's right. I think one of the most joyous things one experiences as a faculty member is when a group of 2 or 3 or 4 students get together, do something, and then come and surprise you with a really nice result.
Exactly.
And you're the next one to know about it.
That's fantastic.
So we have the same culture. So this is why I think I'm here to collaborate.
That's fantastic. Okay, so let's switch. We've got a few minutes for questions, and we've already got one on the Zoom chat. The question is there any concern regarding quantum computing's ability to break existing security algorithms once it matures? And on the flip side, do you believe quantum computing could be leveraged to create new forms of encryption?
Okay, there are 2 issues. One is that in the future, you don't have to worry about it because cryptographers will be always ahead of us. If they know that quantum computers are coming, then they will always come up with something stronger. On the other hand, there are some countries who are collecting all the existing data files right now, and they are encrypted by today's technology. And they may be able to open them, let's say, in 20 years. when quantum computers are developed. So that's my answer.
That's disturbing. Mike, what do you think?
I'll defer to the expert on that one.
All right, other questions? Anyone? Please identify yourself, please. Yes. Wait, sorry, take the mic so that our audience online can hear you.
I'm Barry Greenman. Has any members of the construction or building industry shown interest in materials that could withstand extreme weather and earth events that we've been reading about in the last year or so?
I think construction industry in general is very interested in that because from a risk management standpoint, the insurance companies are pushing them really hard on this, right? And so, in fact, as you probably read in some of the news reports over the last month, that many insurance companies are pulling out of places like Florida. And so naturally, the risk management community is really pushing very, very hard the construction industry to actually improve the quality of materials. And in fact, I just heard a story from abroad that the schools in the UK now are being redone because they're made, their walls are made of porous concrete that was actually modeled after the temporary harbors that were put up during D-Day in Normandy. And so this porous concrete does not last, and so they're crumbling. And so as a consequence, many students are being put out of school just to replace 300 schools. And so, yes, the construction industry is biting the bullet on this, partly because of risk management, also partly because of the politics involved.
Okay. I'd like to say, if we have any students who want to ask a question, raise your hand. Don't be shy. Students, this is your chance. Thank you. Okay, let's take a student question.
Thank you. Matt, a PhD candidate in transportation engineering. So thank you very much. It's fascinating to learn about quantum computing, the future. And if I understand that correctly, that means all the computing algorithm ways to do things would be similar to how we did that or how we are doing them, but just the computer would be faster. So that also means the current algorithms may stay as they are. And we recall like 20 years ago, we have all the machine learning algorithms that were developed, but because we didn't have the sufficient computing capacity, so we couldn't use them. But in the last decade, we saw all the machine learning and data analysis. So maybe in 20 years, when we really have quantum computing, what will happen? Like any kind of potential revolutionary changes, such as machine learning, will happen in 20 years when we have quantum computing?
So I gave many examples of trying to solve the everyday problem in an industry. However, I touched briefly in the last few slides on chemical reactions and so on. Mike has explained to you that the quantum computers are actually perform most efficiently if it is used for quantum mechanical calculation. That means molecule level chemical reaction or drug design and so on. So if quantum computer can actually be implemented at such scale for quantum mechanical simulation of molecules and chemical reactions and so on, then one can also perform deep learning among those atoms made within quantum computers and tell which ones are, useful for certain drugs and so on. So within the quantum world, it can design molecules, drugs, and so on, and it can actually perform machine learning and so on. And that is going to be the revolutionary, but that's going to be, I don't know, 20 years or 30 years or so. But until then, we should try to stick to somewhat more challengeable problem, such as the ones I showed. so that we can contribute to the advancement of the today's computer.
Well, I think part of your question had to do with whether, there's been evolution in algorithms as well as hardware, right? Quantum algorithms are intrinsically different than normal non-quantum computer type algorithms. There are analogies, but they are different in how you approach going from point A to point B, so to speak. So I think there will be developments not only in the hardware, but there will be commensurate developments in algorithmic approaches that will allow one to do things more efficiently and that are essentially intrinsic to the quantum operations themselves, as opposed to the way things are normally done in a conventional computer.
Well, this is great. So we're going to have to stop here and move to a private conversation in the reception. But before we do, I need to congratulate Keio on something else, which is something of great significance. So Keio's high school just won the National Summer High School Baseball Championship. And if you don't know about Japan, this is a big deal. And let me tell you, there are high schools in Japan who spend their whole lives training for baseball. And the idea that the bunch of pointy-headed little brainy kids who think about quantum mechanics would beat all the other kids in Japan is just unthinkable. And there's been a lot of talk about how they did it. And it's actually related to what we've been talking about today, because there's been the players allowed to have long hair and they're encouraged to think independently and not act like slaves or whatever. So really a culture of innovation and openness. It's been a victory for that. And this brings me back to the Northwestern Keio partnership, because there's a long, deep history between Northwestern and Keio that you may not know. Keio's law school's founding faculty member, who was brought by Yuichi Fukuzawa from Harvard in 1889 to found the law school, later became the founding dean of the Northwestern Law School also. And he was a towering figure at both institutions, but while he was in Japan, he actually brought baseball to Japan and played shortstop on the very first baseball team in Japan. So I think we deserve partial credit for what you've achieved. And on that grounds, Megan, do you have our, we've got a little point of this. All right, put it on. Put it on. This is just for the future. This is Northwestern Cubs, because Northwestern Cubs team. So next time, guys, all come back and we'll go see the Cubs. Congratulations, thank you.